So we're going to do a sampling. We're going to talk about the sampling distributions for means. We obviously have made one. What size pen do I have? Fine point, I think that's good. Okay, so this is a purple pen? Forget it. All right. This is section 9.2, I believe, or is it 9.3? Oh, no, this is section 9.3. Sampling distributions. For means. So we got pretty particular yesterday on the sampling distributions for proportions and actually did an application problem. So now we'll do an application problem for the sampling distributions for a mean. The proportions we use if we go out and ask questions like are you in favor of? Do you say yes or is the answer yes or no to certain things? That's proportions. That's categorical variables. When we're taking measurements of things, which we do a lot in social science and we do a lot of in science, we're looking for measurements that we're gonna average. So means are very important, and we did average women's heights, so we'll stick with the heights of average women to do an application problem here. All right, so if my population is of any shape, so normal or skewed or whatever, if the center of this we'll call mu, again, just like we've been saying all along, and our spread, of course, is going to be sigma. It's going to be our standard deviation. The sampling distribution and that's what we have up on the wall there. The sampling distribution has as its center the same number. So from our population and from our sampling distribution, they look like they were both centered in the same place. So it has the same center. And the spread of the sampling distribution, if you look at it over there on the wall, it looks like it is less spread out. It is less variable than the population distribution. Yes, it is. How much less variable? Well, it is sigma divided by the square root of the sample size. N is the sample size. Okay. So that's how I account for making that other graph skinnier than the one of the population. I divide by some number, making that standard deviation number smaller. This calculation for spread is only good if your population is 10 times greater than the sample size. And sample size. Okay, so that's important to check. We have a different calculation for standard deviation. If the population is smaller than that, but we actually don't have to learn that one. Now, my center for my sampling distribution, we're going to abbreviate as mu sub x bar, and the spread for the sampling distribution is going to be sigma sub x bar. So learning the abbreviations there is important because we'll use them a lot. Okay. Now, these numbers are the same whether your population distribution was normal or not. But if the population is normal, normally distributed, the sampling distribution is guaranteed to be normally distributed, or approximately normally distributed is fine. So and there are some other times when the sampling distribution will be approximately normally distributed, but this one is the first thing we'll look at. If you know the population is normally distributed, like we did women's heights are normally distributed, then we know the sampling distribution is normally distributed. Okay, so let's look again at the women's heights. Geez, can I spell? Come from a normal distribution with a mean of 64.5 and a standard deviation of 2.5. If I go and pick out one woman at random, and I want to know the probability that her height is better than, we're doing 66.5 inches. I don't care about the color scheme. So we're going to pick one woman at random. Okay, what's the probability? Her height is, let's say, over 66.5 inches, 5'6.5". Then I think of my normal distribution centered at 64.5. I want her to have a height of 66.5 or more. So I'm talking about the area under this curve with my standard deviation to be 2.5. So, as we've been doing for a few days, I'll get a z-score for that 66.5. So that's 66.5 minus my mean, 64.5, divided by my standard deviation of 2.5. And somebody want to check that out for me, see what you get for a z-score? I can wait until you figure out how to use a calculator. Now you pay like what, $100 and something bucks for those graphing calculators, and it seems like you still don't know how to. I know. That's because he writes programs on them all day long. Yes, sir. The z is 0.8. All right. Michael's awake. Okay. Okay, so now if I want to find the probability that I get a woman over 66.5 inches, that's the probability that I got a z over 0.8. And how do we get that number? You can get it from your textbook, from the table A. You always have the table A's, but I like the shortcut, which is a normal CDF. Oops, CDF. I should be going from 0.8 to positive infinity, and that gives me I'm doing these normal calculations, doing these normal probability problems a little bit, a lot. I'm trying to repeat these because you got to get this into your head. This needs to be second nature after.